as we have the knowledge of random variables, those we have denoted either with the letter small x or small y here. The understanding has been made with the help of 4 experiments into the very first topic that we have discussed. So the experiments were either to flip a coin or to roll a pair die, the roulette wheel also, and one more complex experiment to have multiple pair dies to have been experimented there. Now talking about to switch from these random variables to the random processes here, we can say that the discrete time random processes are nothing but the indexed sequence of the random variables that we have learned so far. So as simply the random variables we have denoted as x or y, we have to provide the index here. In more practical terms, while the digital system is there in consideration, we usually have the indexing by the numbers, and these numbers are basically onto the discrete time axis. Generally, for the representation of the signal into the graphical way, we have the help from 2 axes, those are orthogonal to each other. The vertical axis represents the amplitude level, whereas the horizontal axis can have either the spatial unit in terms of length here, distance, or the time as a parameter. So as we know that the amplitude is continuous with respect to the any instantaneous value of time for the continuous time signal, but that is not the case for discrete time here. We are into the discrete time domain. So we have the discrete values as like starting from 0, we can have 1, 2, 3, 4 and so on like that. Now let us have the random variable that can be thought of a mapping from the sample space of a given experiment. The diagram that we have already discussed into the very first video of this particular chapter. So this is from that particular ensemble to a set of real or the complex numbers here. So in the same fashion, the discrete time random process can be again a mapping from the sample space into the set of discrete time signals, and here the discrete time signals we can denote by x of n here. So here n denotes the discrete time and x is a function of this discrete time. So x of n is the representation of discrete time random process in general. If you take x only, so that time it will be a random variable here. So this was the diagram that we have discussed into the very first topic. So in this diagram, here we have the sample space. The sample space is represented by capital omega, and into the sample space we have the sample elements here. So the elementary events are denoted small omega 1, small omega 2, small omega suffix I in general, and those have the mappings in this particular fashion onto this particular axis. We can have any quantity onto this particular axis, and this is really meant for the indexing purpose. So small omega 1 will be mapped to the random variable x1, omega 2 to the random variable x2, omega suffix I in general to the random variable x suffix I here. So here it is the threshold levels at the lower and at the higher sides. So 0 to 1, the range of the values corresponding to the random variables has been considered here. Now moving further to have the exact random processes to be understood here, let us have again the examples that we have already understood into the first video here. So let us say this is the experiment 1, and in the experiment 1 we have a pair die to be rolled here. So in this particular experimentation, whatever the outcome we obtain after rolling the pair die, let us say for the mapping purpose it will be assigned to the random variable denoted by capital A here. So here the random variable is capital A here. Now when this capital A is allowed to have any integer value between 1 to 6 corresponding to whatever the numbers are printed onto the pair die, the 6 surfaces, so it will be having equal probability for the 6 outcomes here. So this is the pictorial representation of the pair die. Here you can see onto the top side of this pair die we have the number 6. Onto this particular side view we have the number 3. Here we have the 2. So this way 1, 2, 3, 4, 5 and 6. So these are the 6 events, and out of these particular 6 events, for each and every case we expect the equal probability when the die is said to be a pair here. So now the mathematical representation of the random process in this particular example, as just now discussed, will be by x of n here, and now here it can be represented as capital A as a function. We have the cosine function here for n into omega suffix 0 here. So in this particular representation that we have seen, a random process has been created, and it consists of the ensemble of the 6 different and equally probable discrete time signals here. So this is with respect to the example 1 for the rolling of a pair die here. Now we can have another example. We call it example number 2 here. So this example is quite more complicated random process here, and now here we shall consider the experimentation with a pair coin here. We can flip the pair coin into the repeated manner here. So this is the pictorial representation that a coin is flipped. So this is expected to be at the repeated timings here. So here also we can have the representation of the random process by x of n, and n will be the time representation, and every time the expected outcome will be either the heads or the tails here. So as we have already assigned in the case of random variables the outcome for head to be the positive one here, or for the tails to be the negative one, we can have the assignment, and the corresponding random process x of n can be mathematically represented here. Now we shall move to the another experiment that we can call the example 3 here. So in this experiment, instead of having the discrete outcomes here, we consider the continuous outcomes into a specified range. You can recall from the first video of this chapter that it was the experiment of spinning infinite resolution roulette wheel, which has the outcome into the interval 0 to 1, and into this particular interval again the probability is equally to occur here. This is the pictorial representation of the roulette wheel. So this is one of the gambling game here that is mostly found into the European countries here. Now in this particular example 3, if we have any of the number that you can see into this picture obtained as the result of spinning this particular wheel, so we have to assign it to any of the random variable denoted by x here. So let us have the x mathematically represented here. So it will be the infinite binary expansion, and x will be given as, here we have the summation for the index variable n that ranges from 0 to infinity for x of n to the power we have 2 minus n here. So in this representation, x of n is either equal to 0 or 1 when we have the value of n to be always positive, that we can represent it as n always greater than or equal to 0 here. So as far as the random variables are there, a discrete time random process, our topic, is nothing but the mapping from a sample space. As usual, the sample space represented by capital omega, which is having a set of experimental outcomes or the elementary events that we have called it. So it is nothing but the ensemble of the discrete time signals here. So this point is very important, that describes the random process. So Here it is the discrete time random process, and it is the mapping from the sample space of experimental outcomes to a set of discrete time signals. So the thing is very clear. The discrete time signals are there as a part of sample space that usually we denote by capital omega, and those have a mapping to the random process. The pictorial representation of the same concept can be done with the help of this diagram. So in this diagram, here we have the sample space denoted by capital omega, and here are the elements inside. So omega 1, omega 2, omega suffix I in general, and those have the mappings to x1 of n, x2 of n, xi of n. So as we have the representation x1 of n, this is a discrete time signal. Into the very first chapter of advanced digital signal processing, we have the classification between the continuous time and the discrete time signals. If it is x1 of t, it is a continuous time signal. x1 of n mean a discrete time signal. Here it is the horizontal axis marking the discrete time intervals denoted by n. So in all the three representations, here we have the horizontal axis for the measurements onto the n here. Here we have shown a dashed line that is intersecting and orthogonal to this particular horizontal axis and marking n suffix 0. So you can see this is nothing but the origin here, and onto the both sides we have the discrete amplitudes marked here. So these are the various amplitude levels, those we have represented for x1 of n, x2 of n, and in general xi of n. Now there it is, the representation of this discrete time random process into the mathematical way here. So therefore a random process is nothing but the indexed sequence of random variables as shown into this particular diagram, and mathematically the sequence can be written very simply. Here we have the double-sided sequence here. So in this particular representation, you can take x of 0 to be the central element. Onto the positive side, we extend in the direction for x of 1, x of 2, x of 3, and so on. Whereas onto the negative side, we have x of minus 1, x of minus 2, x of minus 3, and so on towards the infinity, but practically there it will be a finite limit here. So in this representation, each of the random variable that we have represented as a part of this sequence is having the underlying probability distribution function. So probability distribution function we have already discussed with respect to the random variable definitions here. So it is represented by capital F as a mathematical function. Into the suffix we denote the random variable for which it is there. So here for the random process, again we take the help for, and it is nothing but we have capital F into the suffix x of n. So here it is the random process. So this is the probability distribution function for the random process, and it is a function of alpha, and the probability onto the RHS is denoted for x of n, the random process, less than or equal to alpha here. So along with the probability distribution function, there it is another function that can be derived from the probability distribution function, especially the derivation is to be carried out for the same, and it is represented with small f here. So it is nothing but the probability density function, and mathematically given to as small f suffix x of n, the random process, as a function of alpha here. So here we carry the differentiation. So dd alpha, here it is the differentiation with respect to the alpha taken for the above equation. LHS has been represented here. So capital F suffix x of n as a function of alpha, the derivation of probability distribution function. So in this video we have introduced you to what exactly the random processes are there. The knowledge for the random variables was very much essential to understand the same that we have already covered from the previous videos here.